Today, we are going to talk about low latency live streaming at scale. We're going to talk about mostly the standards and tools that are available to make that possible. I'm going to stay away from some of the proprietary solutions out there because all the proprietary solutions are essentially built on top of the standards that we'll talk about today in some form or another. So what you learn from this today, you can take to them and kind of sound smart as you're asking them questions about how their system works. So myself, my name's Steve Heffernan, creator of Video.js, open source video player, also co-founder of a couple startups, co-founded a startup called ZenCoder in 2010. We did transcoding in the cloud, required by Brightcove. That included a live streaming API. More recently, co-founder of Mux. We have video performance analytics, and as well as a video streaming API. And finally, helped organize the DMux conference that we had last week in San Francisco. Funny story, I got my tooth pulled last week. Good timing for giving a talk at Zoom meeting, but look at this picture. It's the same tooth I'm missing in the bottom of my teeth. So apparently that tooth was just not meant to be. As a player developer, I'm particularly interested in the concept of low latency live streaming and the idea of interaction around live streaming, because I think it kind of changes what it means to be a video player. Like, for forever we've only worked with the same controls that you got on a VCR, right? Same on the web, like play, pause, fast forward, details like that, right? But with this idea of low latency and interaction, I think it can expand what it means to be a video player, bringing in a lot of those interactive elements. So I don't know exactly what that means yet, especially as what it means for like a player like Video.js to how that might change. But I'm excited for what it means. But yeah, that's essentially the problem that we're focused on is interactive live streaming at scale. So you look at the apps that I have up here. So Periscope, you have the idea of a live streamer on their phone, and their fans can be watching and hitting the little heart button. The streamer sees that and can react to that feedback. With Twitch, you have a video game streamer who their fans are chatting along the stream, and the gamer can respond to what's happening in chat, and the people watching get that feedback. HQ is a pretty popular trivia app where you have a host who's asking questions, and people in the audience are responding, answering those questions, and the host is reading out the results. So you need that kind of like quick feedback with that question and answer. Facebook Live is similar to those. Peloton is a little bit more like interesting in that it's in the health exercise space. So you have somebody on a bike, they're watching a screen, they're pedaling along, and they have an instructor in a classroom remote. That instructor can see how well that person is doing, and they can be like, "Oh, great job, Bob! You're doing, keep it up." And you get that feedback, and you need lower latency in order for that interaction to feel real. What is not? We're not really talking about broadcast media here. So with something like the Super Bowl or the Olympics, you get this. It's more of a lean back experience, right? Yes, you have a Twitter feed going on the side, but it's meant to sit back. You're not interacting with the people on the field or the newscast or anything. You're just consuming the stream. I think probably everybody in this room has heard the analogy. You're watching the game at home and you hear your neighbors cheer for a goal 10 seconds before you see it yourself, right? Be it like a spoiler moment, and that kind of sucks. Yes, that's a real issue with broadcast media, but it's really not as big of an issue as with interactive video. And maybe I'll try to debunk that a little bit. So first of all, with an event like the Super Bowl or the World Cup, they're going to introduce a little bit of latency to begin with, even before the stream leaves the venue. Like, they're going to have some latency in there just so that the director can cut away to a commercial if the newscaster starts going off the rails and spouting crazy things, right? So even before it leaves the venue, you're going to have some latency in there, as much as like 30 seconds of latency. So like they're not even targeting low latency at that point. Secondly, to get to lower latency, no matter what you're doing, you're introducing some level of cost and instability in the network, getting to, like, from the venue to the player. And at a big event, you're not going to take a lot of those risks or that added cost. You're going to stay with something that you know is stable and consistent and reliable. And then finally, the thing that people hate even more than latency and being spoiled is rebuffering, right? So like the worst thing is like they're about to shoot a goal and the player has to rebuffer. And essentially, like, the concept of lower latency is introducing more rebuffering into the chain. It doesn't have to, but you think about the mechanism of it, most of the time what's happening with reducing the latency is you're lowering the buffer that the player is keeping in order to protect itself against further rebuffers. So when you're doing that, you're potentially and most likely introducing more rebuffering for a wider amount of your audience. So certainly not at this point. I can't see anybody streaming the Super Bowl or large event intentionally making that decision until they can feel that like they're not going to introduce more rebuffering by lowering the latency. I think that's just a higher priority. Cool. On the other side, we're also not talking about real-time communication. So this is Google Hangouts, Skype, Zoom, these type of forms of communication where you have audio feedback, so two-way audio. You're really aiming for 0.3 seconds or less of latency. You get beyond 0.3 seconds in that scenario, and you get into you start talking over each other. You get into that like international phone call situation where it's really annoying. So like yeah, you really need to be under that half second, 0.3 second latency realm. And it's different from this like interactive use case in that like I mean, imagine putting 50 people in a Google Hangouts room and expecting them to communicate with each other, right? Like, it'd be kind of chaos. So it's really meant for this one-to-one, many-to-many, but not like huge. You're not scaling up a Google Hangouts room to 1,000 people. Like that's just it's not meant for that. What we're talking about is low latency live streaming at scale, which is interesting because it falls right in between these two things and kind of picks up the challenges of both sides. So, real quick, while building an application like this, one that involves both the viewer interacting and and a streamer who's streaming the video at low latency, you need a couple things. First of all, you need a real-time data framework, and this is built on technologies that have been out there for a while. They're pretty mature. Things like WebSockets, WebRTC data channels, even. These are pretty mature platforms, and there's lots of proprietary services. You have like Firebase and Pusher and PubNub and lots of great services that you can use to help you build an application that makes this, at least the data side of real time, snappy and reliable, so that like somebody chats, like sends a chat message up, and like their neighbor can see it almost right away. I consider that a relatively solved problem. On the other side, we have the low latency video at scale, which we don't really have a solution for. And that's some of the stuff that I'm going to get into today, the standards and solutions that we have at least coming up, and some that you can start playing with right away. Getting more specific on what latency means. Many of you may have seen a similar graph. This terminology isn't perfect, but it's terminology that's like the community has been adopting. Like we certainly were the first to like call these things these names. I think Wow's the first to put up a latency chart. Will Law from Akamai kind of tweaked that with some of the newer mechanisms. But what we end up with, so starting on the left-hand side, we have what we call high latency, right? So 30 to 60 seconds. The interesting thing about this is it's relatively common, especially on the web or iOS devices, because of the mechanism where, well, when Apple first introduced HLS, And remaining in the spec today is a recommendation first to chop up your video into 10-second segments, right? So your video is 10-second segments, and then they say that the player should buffer 3 segments before it starts playing. So 3 segments times 10 seconds, 30 seconds. And that's just in the player itself. So that's not even including the latency that it takes to get from the camera up to the player. And yeah, so latency, we're talking glass to glass. That's what we're referring to here. So that's why high latency is pretty common. But then over the last number of years, people have started to get smart and realize, oh, we can just reduce the length of the segments to start the player faster and reduce that latency. So people are doing 2 to 6 second segments. That is hard to say, missing a tooth. And you end up with 6 to 18 seconds. So multiply that by 3, 6 to 18 seconds at the player, and you start to get that lower latency. As I mentioned before, you introduce a little bit more rebuffering. But if you're aiming for that latency and you have like you feel like your players are reliable, your network for your users are reliable, like that's an easy place to go to. It's an interesting note that you'll see a lot of demos of low latency live streams that are going down to 1-second segments. And that is something you do, and you can reduce it down. You can start to, in a nice demo environment, you can start to get down to around 4 seconds or less of latency. The problem is those demos don't always work so well outside of the demo environment. Once you get to the real world networks, you have this issue of you're making this request every second, and those requests can have overhead themselves. So even just start to receive the data for those segments, can have overhead. We're seeing as much as half a second of overhead. So you're essentially introducing error into those requests that is going to make it even harder to keep up with that stream and harder to not enter a rebuffering state. So what we see when you actually go down to 1-second segments at scale is they start to fall over a lot more quickly, especially on mobile devices and things with more difficult networks. So I don't recommend trying to go down to that. You're certainly welcome to test it. But as you're looking at the demos that claim to get down to this level by 1-second segments, just be wary that in production it might not work so well. So then we start to get into, so with the with the 2-second segments, we can start to get into the idea of low latency. Because you get down to that 6 seconds, and assuming that you have latency from the camera going out to the player less than 4 seconds, then you're in that 10-second range. What I've seen is with these numbers, the 10 seconds, the 4 seconds, the 1 second, they're not perfect, but they start to line up with real-world use cases as far as I've heard people talk about them. And this is going to change over time. But as I talk to somebody who's building a Twitch clone, and they have that chat next to the window, today they're pretty happy with 10-second segments. Of course, everybody wants lower. Everybody wants there to be no latency. But as far as that interaction is involved and the ability to react with chat, for some reason, sub 10 seconds is what people, in my experience, have asked for. And this might be because when Twitch first got started, they had as much as 20-second segments, and people started getting used to this idea of oh, there's 20 seconds of delay between when I chat, when a person says something. And now Twitch is down to sub 6-second range. And so I think that expectation might change as people get more used to that. But today, as you talk to people building these applications, knowing that it's a challenge to get down to lower latency, I hear people asking for 10 seconds. For those type of applications, when you get into something like an HQ trivia app, where you actually have a host who has to whose main job is to respond to what's happening from the viewers, that's when I hear requests for 4 seconds and less. So. Cool. So then we get into this realm of, let me jump over really quick. So jumping over to the end of it, so we have the sub-second latency that I talked about before. this is really the realm of WebRTC. You also have like RTMP fitting into this area. This is the real-time audio communication level. And yeah, those protocols are great for the audio side of things. They're difficult to scale, or I should say they're relatively expensive to scale. Whereas on the HTTP side, which is everything to the left of that, HTTP is relatively cheap to scale, but it's difficult to get down to lower latency. So in this kind of like ultra low latency range, this green bar here is where we have the two different mechanisms kind of competing to be the protocol that is the one everybody uses to get to low latency at scale. So either scaling up WebRTC, using a bunch of media servers versus HTTP, trying to figure out how to hack the manifest in some way to get those chunks into the player as quickly as possible. So moving forward, let's walk through the live streaming workflow and talk about some of the options at kind of each step here. From the camera side, so a few of the obvious options here. So you can start with a camera plus a hardware encoder, something like Elemental. That's a great way to get high quality live streaming video into your network. Other options being desktop software. The most popular desktop software for Twitch live streamers is OBS. I guess that's for Open Broadcast Software, or something along those lines. Really great open source desktop live streamer. And then finally you have mobile devices. You can stream from your mobile device. If you're building anything like a Facebook Live or Periscope, usually this is your only option. As you work down the list here, you're going to become more and more constrained on what level of video quality you can push. With quality hardware encoder, you can push NAP, you can push some of the newer ones, you can push 4K, maybe 8K, and obviously it depends on your network, but that encoder can keep up with the higher quality. As you go down, desktop software, with like maybe your average laptop, you might struggle to stream out a 4K stream and keep the encoder up without dropping frames, without like creating buffer before you even enter the network. And then mobile device, obviously you're heavily restricted on the amount of processing you do, the amount of video that can send out. I think Periscope limits the video that you can send to Periscope to 540p. So just give you an idea of like how some of these services are thinking. Facebook, I think 720p, but like, I don't see a lot of people going up to 1080p, especially on mobile devices. They tend to be pretty locked down on how much you can stream out, both because of the device itself and also because of the network that they're only working with. So then, obviously on the network side, the option of a wired network versus a mobile network. As much as possible, you want to stay away from a Wi-Fi network because last thing you want to be debugging is whether or not when you're seeing like issues in the stream, if it's something outside of your local network or if it might be your local Wi-Fi. Like I see that actually a lot as you have user-generated content streamers having issues with the stream, just like totally confused as to whether or not it's their local Wi-Fi, their local network, their mobile device versus something later in the stack. And of course, the support requests just going like crazy when that happens. But yeah, often with a mobile application like a Facebook Live, a mobile network is all you have, and so you definitely want to be conservative on the size of video that you're sending in that case. Protocol-wise, we have a handful of options as far as transmitting the video from the capture device through the network to, say, the origin. Starting with RTMP. So RTMP is the protocol from Flash live streaming. It's really well supported. It's supported by most anything that streams live. Because it's been around so long, it's relatively stable. In fact, I think there's actually, we had somebody at Demux speak on the origins of RTMP, and they're actually kind of picking up work on it and thinking about kind of revitalizing maybe an RTMP version 2. So we'll see if anything happens there. Next you have WebRTC, which is the kind of newer protocol to the game as far as like open standard in the browser. So you get into details with WebRTC. So first of all, it's not supported nearly as many places as RTMP. So more often than not, you're still using RTMP today over WebRTC. But then there's also an important detail with WebRTC in that it's been primarily designed, well, wholeheartedly designed for this idea of real-time communication and keeping up with the live edge of audio, of video. And so it will aggressively throw away quality. So if it thinks that it's not going to be able to keep up with the quality, with the audio, and if it's going to hit a buffer, like it's going to aggressively throw away that quality. So if what you care about is quality of the stream coming in, even if there might be some buffer in there, and if your player can handle that, WebRTC may not be the best approach for you because just out of the box, it's going to reduce the quality, and you may not like it. Finally, the newer one, SRT. I'm not an expert on the protocol myself, but the stats that I've heard on it is that it's twice as fast as RTMP. We're already talking about real-time protocols here, so RTMP is already pretty fast. We're talking milliseconds here, not seconds. So as we're talking about a low latency chain, that's where we're trying to knock seconds out of it. SRT may not make the biggest impact switching to it from something like RTMP, but if you're trying to eke out everything that you can, it's worth looking into. I'm going to assume that it's supported in way fewer places than RTMP, especially when you get into mobile devices and you get into desktop streaming software, but for your more professional streamers, it seems to be becoming a more popular solution. All right, so and assume we're using a wired connection with RTMP, going into the origin / transcoder. Our first option here is honestly just to pass the video through, right? Like we just pass it from the encoder, whatever's streaming the video, through the origin into the network. So WebRTC does this. Like there's actually, I don't know many solutions that do transcoding the WebRTC stream in the middle and going back out to WebRTC. I haven't heard of that yet. Somebody can correct me there. What actually ends up happening with WebRTC is if you want more like renditions of the video, you're actually creating that on the client. So the client is creating multiple versions of the video, streaming all of those out at the same time. And then as you can imagine, that's kind of filling your network and reducing the amount of quality at the top end that you can send with the highest quality version. But that's being passed through, so you're not doing any transcoding in the center, and it can just go straight out to your network. So there's an upside in that sense. Same with like UGC content when you're talking about a platform like Twitch. So Twitch, where 95% of the views get one viewer, it'd be just stupidly expensive to transcode every single stream that they're getting in. And so what they're doing is essentially taking that stream, they're putting restrictions on what their streamers can send to them, and then they're sending that stream through to their viewers until it hits a certain amount of viewers, and at that point they kick in transcoding to add the different renditions. And that becomes the next option, which is introducing transcoding in the middle, where if you're realistically trying to support audiences out there that are not all just like US based on a wired connection, you're introducing multiple renditions of the video so that the player can make a better decision based on the user's network, which quality of the video should I be playing to avoid rebuffering. What else is there? So our options there are we have a couple of different adaptive manifest options. I'm sure you're all familiar with Dash and HLS. When we get into the low latency piece, there's newish mechanisms that are built into the standards to make low latency possible. So starting with Dash. First of all, Dash has this concept of a segment template, which allows the player to just kind of like know what the next segment name and URL is going to be without having to make a request for another manifest file. So, as a live stream is going, the player is first downloading a master manifest file, which is a text file, seeing where all the different renditions are, then requesting more text files to know where the actual chunks of video are. And each of those steps is essentially introducing latency into the stream or into the playback. And so with this concept of segment template, you can at least skip that second request for a rendition manifest and go straight to requesting the chunks of video. So that's a benefit there. It's also using an approach called chunk transfer encoding. So this is kind of the magic behind the Dash low latency approach. Chunk transfer encoding is a mechanism that's been built into the HTTP protocol forever, like HTTP 8.1, I think. So it was originally used for transferring of big data objects. So think of like you're transferring a big data object to the browser, but you want the browser to be able to start working on that data and showing rows, like say you're listing countries with a bunch of data, something like that. You want it to be able to show like country by country as that data is coming into the web page. And show it on the screen as it's coming down, as opposed to waiting for that whole data blob to come in, and the user's just like sitting there waiting for the data to load, not knowing if it's working or not. So that's what chunk transfer has been used in the past. I don't know why we haven't considered to use this for video until now, but we, with the Dash approach, is using this in order to do basically the same thing. Today, without chunk transfer encoding, when you request a segment, whether it's 2 seconds or 10 seconds, you're waiting for that entire segment to download before you can even start processing and playing the first frames of that segment. So, that's for the 2 second segment, that's close to 2 seconds worth of latency that you're introducing into the chain, just waiting for the segment to download. So what chunk transfer allows us to do is start processing that stream of data and sending it through, maybe it needs to transmux it or just start to decode the video. It can start doing that as the first frames of video are coming in and cut out a couple of seconds to a good number of seconds from that chain. So that's pretty cool. The challenge with this approach, however, is adapting to the stream. So the way these adaptive frameworks work is the player, each time a segment comes down, the player is marking, okay, I'm starting to request a segment, I'm going to measure how long it takes to get that whole segment, and I'm going to see how big that segment is in file size, and measure and estimate kind of what my network speed is off of that. If the network speed is faster than I'm currently playing the video quality at, and fast enough that I might be able to jump up to the next quality, then it can do that. Or if it's noticing like, oh, actually the network's dropping a little bit, then it can switch down to the lower quality rendition. The problem with chunk transfer encoding is that, there's one additional piece of this, in that the player is actually requesting the segment as it's being created. So as the encoder is creating segment 1 and putting that on the origin, these bytes can actually be streamed through all the way through the CDN. So the CDNs will support chunk transfer encoding. It can be streamed all the way through the CDN. So the encoder is still creating the last part of the segment while the player is receiving the first part. So it's being passed all the way through. So that means that it's being passed through in real time. So like the encoder obviously can't capture video faster than it's happening in real life. So it's sending the video in real time, as fast as it can, but like frame by frame as the frames are coming in. So think about that then back on the player side. The player is essentially, assuming you're maxing out as low as you can get on latency, you're only seeing the frames as they're coming in, and the network speed will essentially never be measured any higher than the speed that the video is playing back at. So that introduces this problem of actually knowing when you can switch up. You can still switch down easily, but you're going to end up with a situation where the player just starts to notch down anytime that it sees like an issue, and you'll never work your way back up. There's been a few mechanisms for trying to address this issue, from as simple as finding a cache segment from the past, finding an opportune time to make a measurement, requesting a small chunk, seeing how long that takes, and using that as your estimation. As you might guess, that's not ideal because then you're like using the network like twice, like on the side of the network that's being used to pull the live stream, and you might be impacting the live stream as you're doing that. So it works. It's not the most ideal, but it's one way to kind of start to make these measurements. More recently, there was a paper released, and blanking, I should know the name of it. It was at a Mile High Video, the Comcast event. It's a paper released on one mechanism to do this, measuring these basically these like kind of micro chunks that are coming through the video through the network, and testing to see how. It's really just testing to see if they're cached or not, or if they're coming at live stream or at the line speed or not. So it's got to do with like all this interesting math to kind of average out, like do we think this was cached, do we think this was sent at live stream, or are we actually getting the actual speed of the network at this point? So it's complicated, it's promising. I have heard that some people have tried to put it in production and haven't quite got it to work yet, but it's probably the best approach that we have moving forward to getting this mechanism working. Okay, next line there, LHLS. So I imagine many of us are using HLS. Some of us may be using a mix of Dash or HLS, but if you want to support one format today, you're using HLS because the iOS devices only support HLS. So many people in the community decided, oh, there's this great approach in the Dash side of things using chunk transfer encoding. We should mimic that on the HLS manifest side of things. So Periscope basically kind of open sourced their approach to doing the same thing. So they're doing this in the Periscope application. Twitch also uses the same approach. They've been doing it. They claim to be doing it longer than Periscope had after Periscope open sourced it. But so there's multiple people in the community kind of taking the same approach and now talking publicly about how they're doing this on top of HLS. And it involves a lot of the same mechanisms, being able to pre-request segments that don't exist yet or half exist, and using this chunk transfer approach to feed bytes into the player and playback before the segment's done. So we got close to kind of it wasn't a formalized standard. So the standard of HLS is governed by Apple. And I think Roger might even be speaking here at this conference. But so, any changes to the HLS spec go through Apple. This LHLS spec was kind of a sidecar thing in a hopes to kind of encourage Apple to introduce something like this to the spec. And kind of right as this community version was being solidified, Apple came out with their own approach, which is completely different to the chunk transfer encoding approach. So the way the Apple version approach works is instead of using this chunk transfer streaming approach, you're basically taking these segments and chopping them up into even smaller parts. So think half a segment, maybe even less parts that the player can then be requesting a lot more rapidly, and you've got a whole segment. Like a half second that you can start playing as soon as that one's downloaded, without having to wait for 2 seconds or 6 seconds or 10 seconds before you can start playing. So hopefully you can see how that would enable lower latency. The upside of this, and as I understand it, the reason they didn't go with the chunk transfer approach is that each of these parts is still delivered at line speed. So you can actually measure those parts and get an understanding of what the network speed is and make decisions around how you should adapt. The downside of it is that it does require to really get to the goals of like sub 4 seconds down to 2 seconds, you need some modern networking features. So it relies heavily on HTTP2, kind of two parts of it. One is kind of a persistent connection that the browser can make, or the browser or the device can make using H2 to make lots of these little requests without a ton of overhead of those requests. So that's one benefit of HTTP2. The other is this idea of H2 push. So the way this works is, say I'm making a request for one of these manifests. Well, the server can make a decision that, oh, I see you're making a manifest request for the high rendition. I know you're also going to want the first segment of that high rendition, so I'm just going to send that to you also. So instead of having to make like one request for the manifest and one request for the segment, the server can be smart and just like send that through. And what actually ends up happening is like the player in the browser still thinks it's making that second request, but the browser has essentially like received that first segment, cached it, and made it available to you behind the scenes in the browser. So the player makes a request for it, and it's just there, ready to go really fast. It's a great mechanism. It makes a lot of sense why it makes sense, like why it's beneficial when you're using it in kind of like an environment where you control all these things. It's going to work. I think it's going to work great in iOS devices. In browser land, presents some challenges. One, because this like making tons of requests, the player has to is making 10 to 70 times as many requests as it would with standard HLS. And if you know anything about JavaScript, JavaScript is a single-threaded language, which means you can only do one thing at a time, right? And so if you're introducing this mechanism that has to do something like I think 10 times more than standard HLS, it can start to have an impact on, say, like interactions on other parts of the page. Like the user's trying to click on a button over there, and the player's like making all these tons of JavaScript requests. It can potentially impact that, or the user's like doing a lot of other stuff, like interacting with the video, and that's blocking JavaScript on the page. Well, that's going to block the player then. The player is now not going to be able to make those requests and actually keep up with latency. So that's a challenge that we need to solve with this part-based approach. And the other challenge is, so this mechanism H2 push, as I said, like the browser kind of abstracts that for you, so you don't actually know that something's been pushed to the browser, but then the player is trying to measure that, and the player actually doesn't know if this part was delivered at line speed, and it should measure that when it's making that request, or if it was already cached, and it should throw that out and not actually use that as a measurement. Or it might just be receiving all of the segments as these pushed segments, and it has no idea what the network is because they all look cached. So, call that out. We have some work to do on the Apple version of this approach to understand how it might work in the browser. Otherwise, it's very likely that we end up in kind of a split ecosystem here, where anything in the browser, we're doing kind of a chunk transfer-based approach. Maybe even as far as just everything in the browser is Dash, and then on iOS applications, iOS Safari on iPhones, we're using the Apple LLHLS approach. Cool. Sorry, that was a lot for 3 lines in the slide there. Format-wise, this one's pretty simple. With HLS, you have the option of using .ts files or FFmpeg files, or the CMAF standard. HLS now supports CMAF. The low latency approach supports CMAF. And so moving forward, especially if you're starting today, you should definitely be using CMAF over the TS approach, because Dash uses the CMAF approach, so then it just creates an environment where you can switch if you need to, and it's compatible. Cool. Real quick, this is a photo from a month ago. We had an LLHLS forum down at Apple. Roger was there. Will Law from Akamai, people from Disney Streaming, Hulu, all the major CDNs, and the purpose of this was essentially to try and get alignment between these approaches of the Apple part-based and the chunk transfer approach, at least to make it so that CDNs can operate the same way, because there's a downside of if we're using both approaches at the edge. CDNs would be half transferring things via chunk transfer from the origin, which is one mechanism from getting things from the origin to the edge, and the rest of the time we'd be using this part-based approach, where it's using H2 push and using kind of different server technology. So there's a big push to kind of make it possible for, essentially for the CDNs to use kind of chunk transfer from the origin to the edge, and then make both mechanisms possible at the edge. So it looks like there's going to be a favorable outcome of that, and we'll align at that side. Unlikely that we'll get to a point where we'll align the manifest and the mechanisms at the client. So whether it's chunk transfer to the player or part base to the player, there's kind of no obvious feature alignment there. So I think we were maybe stuck in supporting both approaches for, unfortunately, as I see it, the foreseeable future. If you're interested in digging more into that, Will Offenbach gave an awesome talk at Demux last month. It's up on Twitch, Twitch TV/Demux/videos, called 3 Roads to Jerusalem, the 3 roads being those 3 different manifest mechanisms. And you should definitely check that one out because he's got way cooler graphics than I do. Okay, moving forward from there, so going from the origin, the transcoder, out to the players, we have some similar faces. On the networking side, we use WebRTC, we use RTMP. Interesting story, so HQ Trivia, I assume probably most people have heard of HQ Trivia in here. When they first came out, they were a hot topic. They got a ton of traction. They were making all the VCs in Silicon Valley drool at the amount of users and consistent users they were getting. And our office was particularly excited about it. We would pull up the app every day at lunch and play along. We started inspecting the network traffic to understand what they were doing behind the scenes. We were writing machine learning algorithms to try and answer the questions for us. None of those worked, but it was still fun to kind of play along and kind of see the pickup of how people were getting excited about this game and just the growth, the phenomenal growth that they had. So the fun thing about that is you get, when you inspect the traffic, you start to see the startup behind the success there. For example, all of their CDN traffic, well, they weren't using a CDN for the video at all. And all their CDN traffic for images and stuff like that was served directly from S3, not through CloudFront or anything like that. So that was an interesting thing to notice, just because the performance and the cost and all of that stuff. It's just, you just realize that, okay, they had bigger fires to put out than even optimizing their network. And they were using RTMP for delivery to every single viewer. So they were getting out up to 1 million plus concurrents every single game. So I mean, that's huge, right? The Super Bowl got between 4 and 8 million concurrents this year, and HQ was getting 1 million every day, twice a day, for the months that it was popular. And it's still popular, but I think it's kind of declined a lot. So we did the math on this, and we assumed they were using, I think we either figured out or we assumed they were using a Wowza RTMP server, either that or a Flash media server. This isn't science, but doing the math, we calculated that they were spending probably $20,000 per show just on the encoding piece alone. Then you add the network on top of that, and the other details that come in, and we got to around $50,000 to $100,000 per 15-minute show. So an hour of that is, what does that come out to? $200,000 to $400,000 per hour, right? That's a lot of money to spend. I'm gonna guess most of you don't have that sweet VC money backing you to kind of put that into not optimizing your system. But worked for them. It got down to the latency that they were looking for, and allowed them to scale their audience to a point where they could then start investing time into optimizing these things. But you can see the issue with a mechanism like RTMP and also WebRTC, these real-time protocols, is a couple of things. One is it sets up a persistent connection between the client and the server. And that persistent connection takes up resources on the edge server or the origin or wherever it's connecting to, and makes it, for as long as that connection is there, that server can do less things. Compare that to an HTTP server, so a general CDN edge server. This is going to be commodity-based hardware, and that mechanism is just like, give me this file, okay, I got it, relationship done. And then it like sets up that connection again anytime it needs a new file, but that like releases those resources as the video is going on. That makes it so, I mean, CDNs have been optimizing this for 20 years now, so that's why it's super cheap to stream on a CDN compared to an RTMP or WebRTC based system where you're needing to scale up all these like special servers that are not commoditized and creating these persistent connections. So our general calculation there is to really scale up, and we're talking to like 1,000 people more events. You're looking at the common number I see is 10 times more expensive. 10 times more expensive to scale up one of these persistent connection-based protocols compared to an HTTP-based approach. So you can see why so many people in the industry are pushing for this HTTP-based approach in order to kind of keep the cost down while hopefully getting to a level of latency that works for these interactive experiences. Cool. So then going into the player side of things, on the native side, Android and iOS, you're working with, on Android, XO Player is a great player built by Google and does support, actually I believe it supports both the Dash low latency version and the HLS low latency version in XO Player today. So that's great. On the iOS side, you have AV Player, which will support, well, AV Player supports the Apple LLHLS today. You still have to be whitelisted in order to put the Apple version into production. So today it's you're just testing it, you're trying it out, and then maybe putting it in production when you get permission to. On iOS native, there are ways to build Dash players. You are getting outside of the safety of like the Apple AV Player and networking and all the things that they do for you. And I don't expect most people to do that. I think I see this done with proprietary players, like companies that are building players to sell, or probably if you're Netflix or YouTube, you're doing this. So there's an option to do kind of this Dash low latency approach on iOS. It's going to be really hard today unless you're using one of these proprietary players, which they're out there. Then on web browsers, HLS.js is probably the most popular HLS parser. Dash.js and Shaka Player are the popular Dash parsers. Dash.js supports this low latency approach. I don't think Shaka does quite yet, but Dash is where you're going to see the Dash.js players. We're going to see the most progress on this front, including that newer version of measuring the network for the adaptive algorithm. On the TV side, it's really varied on the TV side. Depends on what is the TV device, or the TV itself specifically supporting in the mechanism of like chunk transfer encoding to begin with. Like does their networking software support that? And then also many of them are built on top of a browser-based like an internal browser-based UI, in which case it's pulling in a lot of the browser features that are already there, but sometimes in an inconsistent way, which is why you have this group, the CTA Wave. So it's a standards group that's working to standardize as more TV manufacturers and TV devices are embedding browser-based video playback into their applications. What are the browser features that we as streamers and player developers expect to be there in that browser, so we can have a consistent environment between all the TV devices. So that's been making good progress, and a lot of the TV devices are starting to align with the specifications that are being created there. Okay, cool. So kind of summarize what I walked through there. So capture-wise, best bet is obviously camera plus a hardware encoder if you can get there. Sending it on a wired network, probably through RTMP today because it's so widely supported. but maybe SRT if you're trying to get to the bleeding edge of low latency. Up to your origin, your transcoder, where you're likely transcoding to CMAF for one, and then using today Dash if you're trying to do this today in the browser and on Android and where else you can make it work. And then today on iOS devices, the best you're going to get to without any of these mechanisms is around 10 seconds. You can do some hackiness in iOS where you call, you really shouldn't do this, but you can call the AV player play API while it's buffering the video to get it to start sooner, essentially, and cut down that latency. You know, seeing other groups trying to do the HQ style trivia thing use this mechanism. So it works, and it can get the latency down a little bit, but you've got to kind of monitor that because AV player will then kind of then try to aggressively if it does rebuffer, it will wait forever to get back to 30 seconds or whatever it's trying to get to. Otherwise, you're waiting for kind of the future where we have this Apple approach to low latency available to us on those devices. Yeah, Android uses ExoPlayer. TV depends on the platform. Great. I think so. I don't know. This took longer than I expected it to. So sorry if I rambled on. I was going to try running a game of trivia with you, but I want to make time for questions before we cut out to lunch here. But if you're interested, I built a trivia app. It's open source. It uses some of these mechanisms. It uses the Dash approach to low latency. It uses FFmpeg to create the manifest, the Dash manifest, and then puts it on the server, and I can stream it from the device. And it's kind of cool. It's fun to play, and you can kind of see not just the low latency mechanism that I'm using, but the real time. I'm using Firebase, which is the Google product for this real time data channel, and it makes kind of that interaction possible as well. If you grab me afterwards, I can show you a demo. And that's it. That's the URL for the trivia game if you want to dig into that. I'm Hef on Twitter, company's Mux. Check out DMuxed. And I think that's it. Thank you. And happy to answer questions.
They will not use the CDN for the algorithm, so what do they back? They just have their own proprietary RTMP server because you don't connect directly to the devices.
Yeah, so the question is HQ. So HQ, if they're not using CDN, how are they getting the video to the people? So yeah, for starters, their audience was primarily US based to start with, and so I think they just had an origin server that had RTMP devices on it that were making connections directly to the end users. It's possible they were fronting that with some kind of CDN that made it not obvious to us that they were using that for the RTMP stream, but it's still making that persistent connection. It would have to be a CDN that still supports the RTMP mechanism, which many of the CDNs abandoned that years ago in favor of HTTP approaches.
And what's kind of
With RTMP, if you're going RTMP all the way through, it's a real-time protocol that will get down to, you can get down to sub 1 second. At scale, you're probably still 3 seconds or below, but that's where these real-time protocols shine, is that latency side of things. Just scaling it up, and the cost and the complication of that is where it becomes difficult. Yep.
So you mentioned Apple's new spec for the low latency HLS and their need for HTTP2. What time CDNs support that?
Yeah, well, if you ask them, all of them will say they support it.
Yeah, so you dig into it.
Yeah.
We haven't found it.
Yeah, right, and there's different ways to support H2 push, and are they actually collapsing requests all the way down to origin, and it's definitely, the one that I hear consistent support, or consistent messaging that they have support for it, and people have tried, is Fastly, so that'd be one to check out. Akamai has some support for it, but Most of these H2 push mechanisms haven't been built for media. They've been built like, the primary purpose for this H2 push mechanism was like, I request an HTML page, and I know this HTML page also has a CSS file and some JavaScript files, and so the server can push those with it, as opposed to waiting for the browser to request each one individually. So CDNs, I think if they support H2, they probably support that piece really well. But this idea of like these bigger files of video and actually caching those things appropriately, and certainly not exposing, like measurements for them or anything. I don't think that's mature really anywhere yet.
So do you think Apple's just end game is to push the CDNs and go support this stuff, or are they going to change their stuff?
Definitely, Apple is trying to push the CDNs to support this stuff better. And this is I mean, like, I'm not in their heads, but like, this is a common Apple look to the future, build for future technology. Get rid of the CD-ROM before anybody's ready to get rid of the CD-ROM. Get rid of the headphone jack before anybody's ready to get rid of. And so it's like they're looking to the future, building for what they see as the future, and going to push the CDNs to essentially make that possible. Yep.
You mentioned an issue with the browser with the smaller main requests logging down JavaScript. Have you looked into web workers or something like that?
Yeah.
Doesn't work.
No, you know what? I have not gone as deep as to. So web workers. So the question is around the many requests for these tiny parts and potentially blocking this like single-threaded JavaScript. One mechanism around that would be the web has concepts of web workers, which are kind of like workers that can run in their own threads. You can do parallel processing, essentially. I haven't tried that out myself. Like, I'm interested to know. The one challenge would be you have media source extensions, which is the mechanism for. You have a video element in the browser, right? And the video element has a feature called media source extensions, which allows you to push bytes into the video element, right? And that media source has to be in the same environment as the video element. And so if you're making requests for segments over, if you're making requests for segments in a web worker, I'd be concerned about pushing all of that data through to the main thread and what that looks like. It could be totally possible, and somebody should try that. I haven't had a chance yet. Yeah. Yep.
You mentioned it's 10 times more expensive reuse persistent connections. That's in terms of number of servers needed or the CDNs?
Number of servers, more expensive servers. Because you think of like, the question was the 10 times more expensive. Like, what's the cause of that? And it's fewer. You need more servers to support the same number of users because you have these persistent connections as opposed to like this quick relationship between the server. And then those servers need to be servers that can support these special protocols as opposed to just like simple HTTP. So that's where I assume most of the expense comes from.
Follow-up questions. Low latency, real-time applications, they should prefer persistent connection.
Should low latency if you are trying, should low latency applications prefer persistent connections? If low latency is your absolute priority, then yes. Like, and if you're building a Google Hangout style application, like latency is your number one priority, you should be using persistent connection. It just the expense of that, like most applications that are doing this interaction type gaming, like couldn't really afford to 10x their costs of streaming. And so, yes, they would rather use a persistent connection that lets them get to lower latency, but the cost becomes prohibitive for them. Yep.
What is the holy grail for the latency? Right now we are down to subsecond. Is it milliseconds? So what's what do you think is the point?
What's the holy grail for latency? Where can we actually get to?
What can we get to, or what at what point just there's no point of pushing?
Okay, at what point is there no reason to push any lower in latency? Well, I mean, like, 0.1 seconds is where you can actually notice latency. So like anything below 0.1 seconds, like, and you know, this is from like science that I've read, people doing testing that like you click a button, like how fast can you, how much can you delay the response after clicking a button to not feel like it was immediate, right? And 0.1 seconds is right where I understand that level is. So like going below 0.1 seconds apparently is not necessary. Maybe that changes when you get into this like audio back and forth situation, but even then, like that's probably the lowest you need to go. For the HTTP-based approaches, though, I don't think we'll ever get below 2 seconds reliably in the near future, just because of everything else that's going on in between. Anything else?